Hello, everyone. I'm Qianbo Huai from Alibaba Group. Today, I will present XFUSE, an infrastructure for running file system services in user space. Implementing file systems in user space decreases dependency on OS and enables higher development efficiency and velocity. However, user space file systems have also been associated with poor performance and RAS support. Here, RAS stands for reliability, availability, and serviceability. In addition, if a file system cannot be accessed by standard kernel interface, application and build changes may be required. There is a large body of related work. For example, XFUSE provides a user space file system framework, and other work improve various aspects of file systems in user space. Our contribution is XFUSE. XFUSE is backward compatible with XFUSE. It improves performance and RAS for XFUSE optimized file systems. XFUSE is designed for user space file systems that use high-speed storage devices and that are deployed in production with strict RAS requirements. For the rest of the presentation, we will briefly overview the XFUSE request flow and then discuss XFUSE improvements on performance and RAS. In the performance evaluation section, we will present parametric analysis of the improvements and the overall performance of XFUSE. When an application makes a syscall to a XFUSE-mounted file system, a XFUSE request travels through, from the application thread to a file system daemon thread via the XFUSE kernel module. After the daemon processes the request, a XFUSE reply travels in reverse direction back to the application thread. Overall, for a synchronous XFUSE request, its completion may involve 2 event waits in kernel. One is for the daemon thread to wait for pending requests if none is available at the time. The other is for the application thread to wait for the request completion. Now let's look at the improvements in XFUSE. During XFUSE request processing, kernel event wait and notification take a few microseconds to deliver. For high-performance storage devices, data may become available sooner than the overhead of an event wait. This observation motivated us to add an initial busy wait period before starting to wait on an event. During the busy wait period, we check if data is available. If not, we yield the CPU and loop to check again. For high-performance storage devices, busy wait yields end-to-end latency as low as 3 or 4 microseconds. However, the effectiveness of busy wait is impacted by a few factors, such as thread placement or the performance characteristics of the file system and the storage. For the busy wait scheme to work under different settings, we want to be able to dynamically predict if busy wait is beneficial and turn it on or off based on the prediction. The dynamic scheme we developed is called adaptive busy event wait or adaptive waiting. In XFUSE, a newly created request is first added to a mount global pending queue. When the daemon thread fetches a pending request, it moves the request to a processing queue. There is 1 processing queue per file descriptor opened on a special XFUSE device. XFUSE introduces multiple request pending queues. It also groups each pair of pending and processing queues as a channel. When a request is created in XFUSE, the file system handler selects a channel for the request. With channels, a daemon thread works on its own pending and processing queues, and thus reducing kernel lock contention with other daemon threads. In later slides, we will discuss channel selection and the performance gain of increased parallelism. Our business requires a fast-paced rollout of new features and bug fixes for user-space file systems. And we want to minimize the disruption to tens or hundreds of months and applications on each host during the upgrade. Our solution is an online upgrade scheme. We extended XFUSE to support online upgrade workflow and state transition. We built an XFUSE monitor service. The monitor service coordinates the interaction between two file system daemons and assists the transfer of file system internal states. The online upgrade feature has already been deployed and is serving our production workload. The figure at the bottom right shows an online upgrade in action. Applications only experienced about 2 seconds of IO freeze when we updated the file system software. Next, we will evaluate the performance impact of the XFUSE improvements. In parametric analysis, we want to understand the effects of policy choices and the tuning parameters, and to project potential achievable performance in XFUSE. For that purpose, we built timing FS to probe individual aspects of XFUSE. Timing FS is built on FUSE low-level API. It can emulate the timing characteristics of different storage devices. With adaptive waiting, we predict at the runtime if a FUSE request or reply would arrive sooner than the overhead of an event wait. If so, it will be worthwhile to bid wait for a short period. Otherwise, we directly fall back to event wait. We gather the latency and throughput data and the different storage types, bid wait periods, and other parameters. Our data show that the adaptive waiting scheme works well for both PMEM and SSD-like storages. The figure at the bottom right shows that for SSD-like slow storages, IO latency becomes insensitive to the bid wait period. Furthermore, SSD-like storage also performs better in adaptive waiting than with just event waits. The benefit is more apparent when the system is under load. And this is because when under heavy load, the daemon thread in adaptive waiting sometimes fetches a pending request sooner than the overhead of an event wait. In production environments where thread placement can be controlled, we can further improve IO performance. For PMEM-like storages and modest workload, if we place corresponding application and daemon threads on different CPUs, we will fully enjoy the reduced latency from bid wait and achieve higher throughput. When bid wait is mostly ineffective, such as those for the SSD-like storages, place the corresponding threads on the same CPU yields better performance. This is because kernel event notification on the local CPU is slightly faster than that across CPUs. When a new FUSE request is created, the XFUSE file system handler decides which channel to queue the request. We experimented different channel selection policies. We found that the best strategy is to evenly distribute the requests across all channels. In addition, we should avoid policies that keep on switching the next request to an idle channel, which renders the bid wait ineffective. Interestingly, a computational chip PID policy performed well in repeated tests. In the PID policy, We simply mod the current thread ID by the channel number. Based on our parametric analysis, we optimized the XFUSE configuration for timing FS and did comparison tests between XFUSE and FUSE. For both PMEM-like and SSD-like storage, XFUSE consistently outperforms FUSE. In system-level performance evaluation, our objectives are to set up a common basis for comparing XFUSE, FUSE, and the regular kernel mode ext4, and to evaluate the performance potential of XFUSE. We use the file bench to simulate workloads. We cover the storage types typical in our environment. Here are the system-level results. For both PMEM-like RAM disk and SSD-like fast disk, XFUSE offers significant benefit over FUSE. For slow disk, performance is bottlenecked by the storage rather than by conduit to the user space. In file create tests, XFUSE outperforms FUSE for both RAM disk and fast disk, but by a smaller margin. This is because of the limitation in the scalability of StackFS and ext4 for the file create workload. To summarize, XFUSE is a FUSE-compatible framework. It enables significantly higher performing user space file systems, and it supports file systems with strict RAS requirements in production. So that's all from me for today. Please contact us if you have any questions. And lastly, we are hiring in our Sunnyvale office. Thank you.